Okay, so in our last video, we learned about 4 different gas laws that we're going to learn to use. Now, if you're in a CP class, and that's what that video is, this video is being recorded for, these gas law equations are all listed for you on your test references. We said Boyle's law is one of the laws you need to know. Now, Boyle's law is listed here, but it's not. There's no label saying it's Boyle's law. But the equation P1 V1 equals P2 V2 is here, and you can see in this list we gave you earlier that's the same equation as we have right here. So that is Boyle's law. Now you have to be able to recognize that and name that, but the actual equation is right here. Charles' law, okay, is V1 over T1 equals V2 over T2, and it's right here on your test references. The combined gas law, P1 times V1 over T1 equals P2 times V2 over T2. It's located, where is that? There it is right there. We switched around V and P, but that's okay. It's the same thing. V1 P1 over T1 equals V2 P2 over T2. Okay? And then the ideal gas law we found down at the bottom was PV equals nRT. And if you look here, you'll see PV equals nRT. Now, if you'll look very carefully right below there, this D equals MW times P over RT, and this MW equals MRT over PV. Those are different versions of the ideal gas law. This is a version, PV equals nRT. This is a version, D equals MW times P over RT. MW equals M times RT over PV. They're just different versions. We've derived these two versions of the ideal gas law from PV equals nRT. We may use those a little later, but right now we're going to stick strictly with PV equals nRT. Okay? Now, just so you know, I'm going to go ahead and tell you, D means density. MW is an old way of saying molar mass. Okay? It means molar weight. Well, weight is not really what's going on. Weight changes, but mass doesn't. So this really maybe ought to be MM, but that's also used for other things too. So after a while, we start running out of letters. This MW means molar weight. This is also molar weight, and M here means the mass. So a mass of some gas times R, the gas constant, times T, the Kelvin temperature, over pressure times volume, is equal to the molar weight or molar mass of a gas. And this is actually used sometimes to determine the identity of an unknown gas. Once you find the molar weight, it's a simple matter of doing the math to figure out which gas it is. It's not hard. It's a nice thing to be able to use. All right, so we're going to use just these 4 equations, Boyle's, Charles, combined, and ideal gas laws, to solve this problem. Okay. Now all we have to do is do the things that you were taught about Boyle's law, and we'll get to that step then where we just figure out, well, which equation is going to work for us to solve the problem. Well, in this case, it says the gas occupies 5.0 liters at 101.3 kPa. What volume will it occupy at 1.7 atmospheres? So we have 3 knowns here and an unknown. Well, you might not recognize that just off the top of your head, but let's list them out. We have a measurement of 5 liters. Well, at this point in the semester, I would hope you know that liters is a measurement of volume. Liters is a measurement of volume. Now, let's just say you didn't know. I would hope you'd know, but just in case, you can look on this list in your test references. And look down here, and there's volume, or there's liters, that's the symbol for liters. There's the name of it, and it tells you right here what it's measuring. It's measuring volume. So I've given you the tools to figure it out if you need to. There's no reason for you to just not do the work and give up and go home, or put your head down on your desk. All the tools you need are there. They're in your test references, or they're in your notes, but you have them if you will use them. So this is a volume. We're going to list it with its variable symbol. Okay, V being the symbol for the variable volume. We also have 101.3 kPa. 101.3 kPa. All right, now you might not know what kPa measures, but you can find it out in the same place. There's our units listed here, along with the dimension of measurement it's measuring. And if you look carefully, there's kPa. kPa is a kilopascal, and this measures pressure. It's one of our pressure units. Okay? So we know this is P. Then we have the question, what volume? That means we've got another volume. Okay, we have a starting volume, we'll call volume 1, and a second volume we'll call volume 2. And now we don't know what that is, so we're going to put a question mark by it. And then we've got 1.7, I need to make some room here, I guess. We've got 1.7 atmospheres. Well, maybe you might not know what that means or what it measures, so we'll look again, and there's atmospheres. And it's also measuring pressure. So here's our P. Well, we've got another P up here, so this must be pressure number 1 that went along with this 5 liters. Those go together, so if that's volume 1, that must be pressure 1. And so now we've changed it when we change the pressure, so this must be pressure 2. We have a bit of a problem solving this because now we've got 2 different pressure units. We've got to convert one to the other, and we'll talk about how to do that in a minute. First of all, let's just using the variables we have listed here, let's figure out which equation we're going to use. We've got 4 to choose from. We've got Boyle's law, P and V. Well, this is P and V, isn't it? So this is the equation we're going to use to solve this problem. Okay, we're going to list it out. It is required that you make a list of knowns and unknowns with the variables, and then you write out the equation that fits those. So P1, V1 equals P2, V2. So now that we found the right equation, we've written it out, we're going to plug in. We're going to plug in the known values that we have. Well, we have a pressure here, and we have a pressure here that's going to be different. So what we need to do is to convert either this one to atmospheres or convert this one into kPa. And it doesn't matter which way you go. Either one will give you the correct answer. Well, how do we know how to convert? Well, it's also in your test references. This shows you that 1 atmosphere is equal to 101.3 kPa. So that's an equality statement. And with an equality statement, we can build conversion units. And with conversion units, we can convert from one measurement unit to another. Okay? So let's see, I've got 101.3 kPa. I'm going to put it down here, 101.3 kPa. I'm going to look at this equality statement right here. I see that I've got 101.3 kPa on this side of the equality statement and 1 atmosphere on this side. I want to match the units of measurement down here. Well, I don't want to put a decimal place here. It should be 101.3. So in this equality statement, 101.3 kPa goes to the bottom. 101.3 kPa. And if that side of the equality statement is on the bottom, this side of the equality statement goes on the top. Okay, well, I've set it up so it's really easy for you because 101.3 and 101.3 are the same thing. They can cancel out. The units of measurement kPa are the same on top and bottom. Those can cancel out. And so all we're left with is 1. So now we know that this 101.3 kPa time, well, we cancel that. It's only 1 atmosphere. So this now we can say is 1.000 atmospheres. So now we're ready to plug in. We've got our matching units of measurement. I want to do that. It's up here. Put it in the wrong place. This is equal to 1.000 atmospheres. Okay. All right. So 101.3 kPa turns out it equals 1 atmosphere. 101.3 kPa equals 1 atmosphere. So now we're ready to plug in the values. I'm going to kind of move down here just to give myself some more room so you can see what's going on. Alright, so in place of P1, I'm going to write the value for P1. I'm going to say 101.3 kPa. In place of V1, I'm going to write the value for V1, which is 5.0 liters. Okay, and there's our equal sign. And then we've got P2. P2 is 1.7 atmospheres. Wait a minute. We want to change this to liters, don't we? Because we can't use atmospheres and atmospheres. Okay. Let's make sure we use 1 atmosphere then. 1.00 atmospheres times 5 liters. And now it'll match the atmospheres we're going to use with this one. And then V2 we don't know, so over here we're going to leave that V2. So our first step was to write our list of knowns and unknowns. Okay. Our second step was to choose the right equation and write it down. Our third step is to substitute the known values into the equation. And then the next step then is to get our unknown by itself. Well, the unknown is what is in the equation that's just the variable symbol. In this case, it's V2. We want to get it by itself. Well, what I have here is 1.7 atmospheres times V2. In order to get V2 by itself, I'll have to divide out 1.7. Division undoes multiplication. So I'm going to put this over 1.7 atmospheres. But if I do it to this side of the equality statement, I must do it to this side. Otherwise, the equation is no longer actually equal. And by doing that, you should be able to see you can cancel 1.7 because it's exactly the same on top and bottom. You can cancel atmospheres because it's the same on top and bottom. And we can simplify the left side of the equation by canceling out atmospheres. We're ready now to actually do the math. 1 times 5, 1.00 times 5 divided by 1.7. And I get 2.941176,471. And I have units of measurement of liters. And over here, that's equal to our V2. So that's the unrounded answer. We need to make sure we round to the correct number of significant digits. And you find the significant digits for an multiplication and division problem by looking at the measured and calculated numbers, and only the measured and calculated numbers. Well, this is measured, that's measured, that's measured. Although we could say that was actually calculated because we calculated it from 101.3 kPa. Either way, we're looking for measured or calculated numbers. This is measured or calculated. And find the numbers or number that has the least digits. Well, both of these have the least digits. There's only 2 significant digits here. And then so we want our final answer then to have the same number of digits as the measured or calculated number with the least digits, which means we want our final answer to have 2 digits. So we're going to underline everything after our first 2 digits. We're going to use an arrow to show a rounding off. And then the rounded answer is 2.9 liters equals V2. Now, this is solving a problem for Boyle's Law. And we've already done a Boyle's Law problem. I'm just doing this as a reminder. So our next video then goes to another problem. We're going to find a different problem with having to use a different, or maybe using, you'll have to figure it out actually. I'll do it with you and then you can do one on your own. We'll be figuring out how to use this then to solve for other kinds of gas laws.